and talk is on pruning redundancy in answer set optimization applied to preventive maintenance scheduling.
Nothing is visible. Ah, interesting. All right.
There
fine.
you go. Okay.
All right.
It's all yours. Go ahead.
So in this talk, I will discuss maintenance of machines and describe some concepts what we have used in our simplified kind of model, conceptual model of the problem, and then define a particular optimization objective what is derived or presented in the previous paper. This conceptualization and the objective gives us the background for the current research where we try to improve the efficiency of ASP solver in this particular case. And then I present some experiments and conclusion. So preventive maintenance scheduling relates to this kind of phenomenon in various kind of machineries where we have different kind of things going on in failure. Some components will fail in the beginning of their lifetime just for kind of early infant mortality or burn in reasons, or then there are random failures and then wear out failures. So this last one is focused in preventive maintenance scheduling. So it aims to maintain good health between maintenance breaks and kind of select those maintenance breaks and what to maintain during those breaks, so that we never would enter to this kind of situation where components wear out for their age. So all aspects of failures are not targeted by this problem. In multi-component machines, there are many dependencies between components, and it is typically the case that when you want to maintain one component, you actually have to stop the whole machine and maintain perhaps rationally many parts of a machine. So it's unlike the situation of a factory where you have multiple machines, and then if one machine is maintained, you can still use other machines. So this kind of holistic approach is needed for big machines like paper mills, steel factories, and even cars, trucks, and even more familiar things. Preventive maintenance scheduling has actually been studied quite a lot. Maybe the body of research is at least 1,000 articles, but there are three kinds of solutions. There are local solutions, and then which are more or less approximating as well, but then exact solutions or global solutions, which are pretty much harder to obtain. And of course, due to various parameters and aspects to include to this problem, there are a lot of different formalizations and also these kind of methods, genetic algorithms, MIP, dynamic programming, and CSP, and so on. They have been used earlier, but Also, ASP or answer set optimization is also well suited for solving scheduling problems and planning problems. And in fact, this preventive maintenance problem is not a typical scheduling problem, because you don't want to compress the make span of production, but you want to make the components and machines to last as long as possible. So it's a slightly different perspective. Then just recently, we, with one of the co-authors, we formalized so-called miscoverage preventive maintenance scheduling, where we have a particular kind of objective function, and it is based on simplified formalization of a problem, and we showed it was NP hard and provided a baseline encoding for that. So I would like to now call your attention to this part of a slide. Here you have a formal definition, but I'm not going through this. Instead, you get the idea when I explain this grid here. So a schedule is here is two components. We have a schedule, which is kind of plan for maintenance during this timeline of, let's say, weeks or equally the units of equal duration. So there are 32 units of time, and then these blue lines here indicate breakpoints where the machine is closed and we can maintain it. And then there is a parameter which tells how many of these blue lines we can have. In this case, we have set the upper limit of 8, but we only have 6 in the picture. And then for each break, there is a selection of components which are maintained, and that's the idea of the schedule. And then in these schedules, if you do not ever maintain the component, and already when you start the machine, it's in the beginning, it's kind of in bad condition, then all cells or time points will appear as red boxes. But if you actually have a breakpoint and you choose to maintain a particular component, then if we have this kind of service period of 3, then 3 boxes will turn into green. And then also it is possible to observe the situation in the beginning and observe the condition of a machine. And then in that case, we can set the initial lifetime for each component, how many boxes we will have, or how time units we can still use that component before servicing it. And then if we actually do these both things at the same time, so that we have some usage time for the component, and then during the last time unit we start already, we service it, so we actually lose that available remaining lifetime, and then we will show it with this kind of blue box. So this is our representation for the coverage count over the schedule. So now based on this notion, we define the objective function. In this example where we have just one component and then schedule for maintaining it, you see that there are a few breakpoints. It's hard to see these blue lines, but we will service the component in these places where we have S. And then starting from each service, we have 5 boxes of green, unless it is overlapping the next one. And then here we should have serviced, but somehow we missed that. And we took quite a lot of risk running the machine without proper component. So now from this coloring, we can compute how many red and blue boxes we have, and that gives us the measure what we call miscoverage of the schedule. So we generalize this to case of multiple components, and then we again compute over all the components how many blue and red boxes we have. And one important thing to note here is that all components are part of one single machine. And if a machine is stopped at this point, then we can service multiple components. And no component can make exceptions. They have to share these breakpoints. They cannot have their own individual ones. And this makes this task harder, at least NP hard. And because it's so hard, ASP is not very scalable, and we have to do something for this. We do not want to approximate yet. Instead, we looked how to prune the search space. And we actually found 6 ways to kind of remove from the search space of the solutions those which are somehow symmetric to a similar solution, or otherwise they are even worse than some other solution. And we call these properties of prunable schedules with this kind of terms like schedule can be lagging, congested, underserving, and so on. And once we introduced these properties, the capstone theorem of a paper is actually saying that we can remove all of these all schedules which have any of these properties or many of them at the same time, whatever. But we can do the kind of pruning at the same time without reducing the last optimal solution from the search space. And then we actually show that it has been implemented. And so I will now go through those pruning constraints. So first class of schedules which can be pruned are called lagging. And if you look at this schedule, you see that at time point 8, we have components which will be serviced here. But just before that, all of them have been used for one time unit without any more guarantee of a good condition. So they are like stretched over the good using time. And it's like of lagging behind. The service is going too late. And in this case, we get better solution if we move this breakpoint one step backwards and then schedule again from that point onwards. So you see that the miscoverage between these two schedules, it improves. And so we can prune this first one. And now if we take the same thing, but in the opposite way, that we have service too early, so that now we have kind of the service periods are overlapping. So we could have gone still one more time unit with the previous components. Then in that case, we can move this breakpoint one step further. And again, we get improvement. So the schedule which is still left in the search space is better than this one, what we will prune out. Then we have what we call underserving schedule. And in this case, we consider a time point 1, and then in the maintenance interval for this particular component is 5 time units. So if we would have serviced here, like we do actually here, we would have kind of done it a little bit too early because there is still some lifetime left. But still, these 3 boxes here would turn green. And then again, this one turns blue. But it is still like a trade-off situation that we get more green than we lose. And that way, it is beneficial to select this one. Okay, we don't select it by constraints. We just leave it to the search space. But we remove this one from the search space to make it easier to find it. And then other way around, we have here 2 quite close service operations. And if we remove the first one, we just get 2 red boxes. And instead we win when we change 3 blue boxes to green ones. And in this case, the schedule is called overserving schedule. Then there is undertimed schedule. And in this case, consider the time moment 1. And again, there is this maintenance interval is 5 time units. And let me try to get to the flow and remember what was this thing. Actually, if you are awake, you can help me. This is also a good practice for your understanding. What is the difference between these two? So we observe here that there is a possibility, there's a breakpoint here, but we didn't use it. We could have done this service earlier, in which case there would be more red boxes here, right? If we just change these earlier. But what happens if we move this whole series of green boxes earlier? Then there will be kind of chain effect, and then other things will happen as well. So this one here, these 5 boxes, these will move here as well, because this moves backwards. And then it gives us really nice improvement, like here, by doing this in several places, we actually obtain 2 boxes benefit. Again, this is all obtained by eliminating possibilities from the search space. And last one is just the opposite. Here we have overlap, and if we shift the whole thing to the right, then it becomes better schedule than this oversight. And thanks. The capstone theorem just says that we can do pruning of all these kind of under optimal schedules at the same time. We have developed for the basic case where we do not do any pruning, we have developed 5 different ASO encodings. And in the previous paper, we published the 2-level encoding. And in this paper, we published this elevator encoding, but it's already available otherwise. It already existed. And here is just very simple idea that we have the limits for, or we specify how many components we have, the timeline, and what colors for the boxes we have, and then we have some kind of planning-inspired approach where we start from the beginning of the schedule and we kind of just compute in a deterministic way that given, okay, there I don't show the choice or selection rules which choose those breakpoints and choose the maintenance operations for them. But when we do those, we just deterministically fill the schedule with colors and compute the miscoverage and minimize over that. And then we just added these pruning constraints to each of our encodings. So we have 6 pruning constraints for each of those. And we then performed experiments with a cluster of CPUs. And the first observation was that when we used clasp solver, there we compared branch and bound optimization strategy against unsatisfiable core strategy. And so this is branch and bound, and this is unsatisfiable core. And so unsatisfiable core was already before much better. But when we do this pruning, suddenly this branch and bound becomes very much similar to the better strategy. And still, if we do both improvements, so we use unsatisfiable core and do pruning at the same time, we get best results and can actually solve all 160 examples. So on average, the performance gain is 10 times speed up. And this actually is true in 2 cases. One is that we introduce more components to the machines. So the machines are growing, more complicated, or we introduce more time steps to the timeline. So in both cases, the problems are getting harder, but also the pruning is doing its job in a similar way. And then we also did same experiment for all encodings and found that all encodings improve with pruning. And then we also compared this to LASP solver. It was slightly slower than CLASP, but still they were similar kind of trend for all the encodings. That using pruned encoding or pruning rules constraints, we improved the efficiency quite a lot. And then also we compared the situation that when we grow the timeline or we grow the machine, do we actually do the pruning work only for small examples, or do it work in a similar way? It's very similar experiment to the previous what I showed, but this shows that when the number of time steps grows from 16 to 64, the complexity time requirement of a solver grows exponentially, but also the improvement of use based on the pruning is very similar. And then for the experiment, another experiment where the number of components in the machines grows, we have very similar trend, but it is less smooth. So conclusion is that this miscoverage PMS problem is an interqueuing challenge for answer set optimization, and the contributions of the current work are that we have applied a principled pruning based on problem structure, that pruning breaks symmetries and eliminate non-optimal solutions. And we then have a theorem to prove correctness of pruning. And in general, the gained performance improvement was tenfold on average. And it was stable for different situations where we changed solver, we changed search strategy, we changed encoding, and we scaled parameters. But there's one warning. If we add more constraints to the actual preventive maintenance scheduling problem, like timing constraints, vacancies of service personnel or other kind of constraints, then it is no more guaranteed that we still get the optimal solution with these constraints. Thank you.
Thank you. Any questions?
So I had a question. When you were going through the examples of the symmetries and like the over constrained and under constrained, are the red and blue boxes always weighted the same? Because like in this example, they're all weighted the same. What happens if they're not weighted the same? Because it seems like having a part B overserviced would be maybe better than having it break down.
Yeah, good point. They in this current the definition of miscoverage doesn't have weighting, but you make a good point by saying that the weighted case is very important.
Okay, thanks.
Thank you for your talk. And my question is about the benchmark set. So could you explain what kind of benchmark set do you use for evaluation? So it's a random instance or some standard benchmark set of this problem?
Okay, they were random instances. We tried to check that the machines have different components there. The same component is not repeated. And then there are, for example, for different size of a machine, for each size, we generated 10 random machines. And then those same machines were used in all experiments consistently. So it gave us Wait a moment. Oh, here we have for time steps. Also, when we introduced more length to the timeline, we had 13 different lengths, so it gave us 130. And for the the biggest machine was, I think, 16 components.
Okay, thank you.
Any other question?
Yeah.
Yeah, sure. Sorry.
Please go to the slide for the cactus plot.
Sorry?
And the cactus plot that you show
Yeah,
the plot.
cactus plot, yes, of course.
Usually cactus plot is used for the decision problem.
Yeah.
The number of solved instances. You mean the x-axis means the number of the solved instance for optima, you mean?
Yeah. All of them are, we are solving global or exact optimization. And there was timeout. We couldn't solve all of them. And in these cases, the timeout was reached quite early.
So just the number of optimal solution.
Yeah, of course, we can find approximate solutions with some other approach, but to find optimal solutions and kind of prove it with ASP, then that was the complexity.
Okay. So do you have any result for comparing the somehow the value of objective function?
So,
yeah, because the usually optimization problem, we compare the quality of the optimization function.
Yeah, that's a good point. We could actually start approximating to get reasonable solutions in a reasonable time.
Okay. Thank you.
Thank you. I'm looking at the time, and I think we should stop for the coffee break. So let's thank Anssi again.